Hi, welcome to this lecture on heaps. My name is Dr. Ritesh Ojira. So what is a heap? A heap is a binary tree, storing keys at its nodes and satisfying two properties. So this is the first property and this is the second property. The first property is called the heap order property. Now you could have two different kinds of heap order properties depending on what kind of heap you are trying to design. You can have a min heap or max heap. And that will affect the choice of the heap of either using a min heap or max heap will affect the choice of the heap order property used. Okay, so the min heap order property is what I'll be talking about in this lecture, but in no way is this property applicable to the max heap. So you just have to transfer. So let's look at the min heap property. So the min heap property says for every internal node V, any internal node. Okay, so remember what an internal node is. There's internal nodes and external nodes. External nodes don't have children. Internal nodes do have children. So for every internal node V, that includes now 2 and 5. Okay, other than the root, all right, the key of V is greater than the parents of those nodes. So that means here 5 is greater than the parent 2. You see, the key of the parent. So this is important, and it also extends to the external node. So you have here 9 is greater than 5, 7 is greater than 5, 5 is greater than 2, 6 is greater than 2. Okay, so this is for the min heap. In this case, you can see the minimum is on top, the smallest value is on top. If this was supposed to be a max heap, then the max heap order property will reverse this. You'll just change the greater than equal to or less than equal to, and there your key value will be smaller than the parent value. So if this was a max heap, then this value will be smaller than this value. This value will be smaller than this value, and so on. And in a max heap, your largest number is at the top. In this heap, which is a min heap, your smallest value in the collection is at the top. That's important. So the other property is just that it's a complete binary tree. All right. So that's what this says. It's a complete binary tree, and this part of the complete binary tree is not really necessary for a complete binary tree because it just has to be height balanced. But this property tells us at depth h minus 1, the internal nodes are to the left. That means that you don't have a node here. Right, you don't have a node there. Why? Because it must be leftmost. So 7 here is the leftmost node. Okay, if 9 wasn't here, then this would have been violating this property. Okay, you can add a node here because then this will be leftmost. Okay, so the nodes at the last layer, the last layer must be leftmost. So you can have that, but you can't have this. You could have had the situation where 7 wasn't here because then 9 will still be leftmost. You could have the situation where 9 and 7 weren't here because then 6 would be the leftmost on the last layer. So this is important because I see a lot of students get confused with this last property over here. And it's important. I think the more exposure you get with heaps, the more obvious it becomes that this is necessary. So always remember that number 1, it needs to have the heap order property, and the heap order property says that you must have this parent-child relationship depending on whether it's a min heap or max heap. And the other property is that it must be a complete binary tree. And if you don't remember what a complete binary tree is, I've discussed this in the section on trees, which was the last lecture, or the lecture before the last lecture. Right. Okay, and the last node of the heap is the rightmost node of the maximum depth, right? So that's in this case is 7. If I just remove these, it'll be 7. Okay, that's the last node. That's how I've labeled it here for you. Okay, that brings us to the height of a heap. Now, this theorem just tells us that the height of the heap is log n. I have explained this already, so I'll go over this. You can just go back to the lecture on heaps, on complete binary trees, which is what the lecture on trees, and you'll see that we had this really cool property where since it's a binary tree, the number of nodes here was 2 to the 0, which is 1, then the number of nodes here is 2 to the 1, the number of nodes here is 2 to the 2, the number of nodes in the next layer will be 2 to the 3, and the reason we're just always doubling in size, because we're always doubling. I mean, you can see the analogy, one node gives 2 nodes, one node gives 2 nodes, one node gives 2 nodes, and so we always are doubling. And if you add this up, with the exception of the last layer, you'll get your log n, which is for h minus 1, because you can't guarantee that there'll be a full layer here, all right, and that'll give us the approximation log n. So what you should take away from the slide is, well, after going through the section on the height of a complete binary tree, from the other lecture, I want you to take away from this slide that the height of a heap storing n keys has the height of log n, and this can be deduced by looking at the number of layers and then just summing it up. Okay, so that's important, and you'll find also in that lecture other properties such as representing the height with respect to n, representing the height with respect to the internal nodes and external nodes, and you might need that to answer some questions. Great. So then that's important. Right. So we spoke about priority queues, and we see that in this lecture, I'd like to now present a better way of implementing priority queues. So in the last lecture, I spoke about using things like unsorted lists and sorted lists to implement priority queues, and we saw there was a trade-off. Using the unsorted lists, we had a trade-off in complexity between insert and removement, and using a sorted list, we had this similar trade-off of complexity between insert and removement. But the point was that one was not better than the other, because they both gave us the asymptotic quadratic time complexity, which is a problem. Quadratic time is something we'd like to avoid, especially for the sorting algorithms, selection sort and insertion sort. We'd like to avoid these higher order complexities like quadratic time. We want to go more. The closer we get to constant time, the better. We might actually be able to show that we cannot perform a sort in constant time, but we can strive towards it, like producing such sorting procedures instead of quadratic time, such sorting procedures like logarithmic. We might also be able to show that a sorting procedure can never be logarithmic, but maybe n log n would be sufficient. And you'll find that heap sort, which is what I'll introduce you to in the next few slides, is n log n. It's in a fantastic algorithm, and this is now the cutting edge in terms of sorting, in terms of sorting procedures, more revolutionary approaches to sorting. And we find there's other very popular methods that also make use of this notion of trees, such as merge sort, that gives us also logarithmic n log n. And there's lots of these great sorting algorithms. So if you do want to use a sorting procedure, don't use things like selection sort or insertion sort when you have large lists. You rather use things like heap sort. Those selection sort and insertion sort are very good if you are on a very quick algorithm that is for very small input sizes. Those are very good because it's quick. But in terms of providing sorting procedures for larger sequences of lists, or sequences of numbers or objects or whatever the case might be, if you've got larger sequences, you rather put in the time to create a heap sort or a merge sort, and so on. So let's discuss heap sorts in this lecture. Okay, so we could use heaps to represent priority queues. All right, so before we spoke about sequential lists to represent priority queues. Now we're speaking about using heaps for priority queues. Now, those of you who know about stack memory and heap memory, now it is true that stack memory follows the analogy of the stack, right? It looks like a stack is how you would structure variables in a stack-like way when you're dealing with stack memory. But heap memory and the heap data structure have absolutely nothing to do with each other. Nothing whatsoever. Heap memory is just a large collection of space that you can use to declare variables, and that's something that you would have found in the earlier chapters in the textbook. But the heap data structure is not heap memory. The heap data structure is a way of organizing your entries to be able to perform some efficient things. So we'll discuss those things in this lecture. So let's quickly, I just wanted to put that out of the way because that's very important. I don't want anyone to think that the heap memory and heap data structure is the same thing. Okay, so we can use the heap to implement a priority queue. We see that. Let me just highlight that. We can use a heap to implement a priority queue, and this will not be a sequential list. So in this case, we store, instead of having these nodes, will have this will be represented by objects with the value and the key pair, as we saw before. So you got your key. And last time we referred to them as values, but we can also refer to them as elements here. So your key here, for example, 5, and your element is pet. Your key here is 2, element is Sue. Key here is 6, and the element is Mark. And you could, this figure shows them represented as pointers, but yes, you could have these little nodes that are pointers to types of these kinds of objects. And you know how to define that. I'll just quickly write it for you. You can just say things like node, new node is equal to new node, and you can create your constructor here, whatever the case might be. You can have a key and a pet, something like that. If you define a class node for this, okay, this is just going a bit overboard describing this, but this is just if you really want a more concrete understanding. You can create new nodes like this and arrange them in a heap. But I'll tell you now how to do that. So we'll also discuss implementing heaps in this lesson. Okay, great. So we need to keep track of the position of the last node, and we do that because depending on what implementation you use for the heap, you would allow different kinds of computational burdens to keep track of the last node. But it's always a good idea, because inserting items into the heap involves that last node, and removing items from the heap involves that last node. So it's important that we keep track of the last node. There is an algorithm later on that you can use to find the position of the last node, and I will show you that a bit later on. Okay, right. So insertion into a heap. So inserting into a heap is not very obvious. Okay, so suppose you've got your heap structure. So let me convince you that this is a min heap. So you got 2, right, which is less than its children, 5 and 6. 5 is less than its children, 9 and 7. 6 doesn't have any children to be less than, but if it did, it would be less than its children. And this, so then it holds the first property, the heap order property, and the second property, it's a complete binary tree, so check. And the last one is that the last layer needs to be leftmost. They need to be to the left, and indeed these are all packed to the left, so that's perfect. If there was another node here, that would have been fine. Let's create one just for the sake of showing you that it is possible to have another node here, and this node will be let's make it 10 comma a Judah. Okay, seeing that these are names. And yeah, that's how you could have another node here, and then this would be correct because 2 is less than its children, 6 is less than 10. Okay, that's important. Okay, you see that there's a partial ordering, unlike before, a total ordering, but that's a topic for another discussion. Okay, so insertion into a heap. So how do we insert a new item into a heap? Well, to insert a new item into a heap, suppose you want to insert a new item K, a key K. So all you've got to do is make your way to the last node. This is the last node, right? The insertion position. Okay, once you've got that, then all you've got to do is simply so you can create a node, so a new node, you create a node, all right? Then you store your K in that position. So we created a new node, our K here is 1. We store our K in this position. And then we see if it violates the heap order property. We look at this layer. So we look at this 1 that we've inserted in the last node, and we see if it violates the heap order property. And indeed it does, right? Because the heap order property never says that, I'll go back to it. It says here, the heap order property, let me highlight it. The key must be, the key of a value, the key V is greater than than the parent. It's greater than the parent. The key is greater than the parent. The key is greater than the parent. Okay, but here the key is not greater than the parent. So it violates that property. 1 is smaller than 6. So what do? Well, we just restore the heap order property by upheaping. So what do we do when we upheap? So we add 1 at the bottom here. All we do is we compare it to the parent, and if the parent is greater than the child, we just swap it. We swap it. And so the 6 goes at the bottom, the 1 goes at the top. We call this upheaping. Now we are here. We're pointing to this instance. Our mouse is here. This is the pointer from our algorithm. It's pointing here. We now look at the parent. The parent here is a 2. 2 is greater than 1, and this is a min heap. So it violates the heap order property. So we need to swap 1 with its parent. So we swap 1 with its parent, and we have now restored the heap order property. We now need to check, is the heap order property, we look at it, yes it is. So 5 is less than its children, 1 is less than its children, 2 is less than its children, and so on. So we've re-established, we've restored the heap order property, but that begs the question, what was the complexity of this? So looking at this, we think, okay, goodness gracious me, how am I going to analyze the complexity? It's well, it helps that it's complete binary tree, and we know that how many swaps, we would have to figure out how many swaps would we need to do. So you think about this. I'll give you 1 second to think about it. If I started here, how many possible swaps would I need to do? Well, I would have to do this one. And in this example, we did all the possible swaps. We swapped from the bottom to the second layer, the third layer to the second layer, then from the second layer to the first layer. So we did all the possible swaps. It could have happened that the heap order property was restored once we did the first swap. It's very possible. It's very possible that that could have been the case. But it wasn't, right? Suppose we inserted a 3. If we inserted a 3 here, okay, instead of a 1, then we would have swapped the 3 with the 6, and then we would have been done. We wouldn't need to swap the 3 with the 2 because 2 is less than 3. So my point here is that the heap order property can be satisfied halfway through swapping. Okay, but we are interested now in calculating the worst case, which is what is the possible path that it would need to take to get from the leaf node right to the top. And we know it's a complete binary tree. And the height of a complete binary tree is log n. So we would just need log n steps to get from the bottom to the top in the worst case. So in the worst case, we go from the bottom right to the root, and the length from the bottom to the root is log n because it's a complete binary tree. So that's how we get our complexity. That's the analogy, right? If you want now a proof of why is the complete binary tree log n, then I refer you to the Lakshon trees. Okay, now that we know how to insert elements. Okay, so now looking at this, you can insert elements. Okay, so where would you insert? If I asked you to insert a 3 here in this new, in this heap, so I'm just going to scratch this one out. Have a look at this. If I ask you to insert a 3, how would you do it? You would insert the 3 here. All right, then you check, is the heap order property satisfied? Yes, it is. It is, because 2 is less than 3 and 1 is less than 2. Then we can insert another one. So let's try to insert now a 4. So we insert a 4, we do it here because remember we need the bottom leftmost position to be the insert position. So we insert it here. And then we see the heap order property is violated because 9 is greater than 4. And 4 is not less. 4 should be on top of 9. So all we do is we just move 9 here, we move 4 here. We see if the heap order property is satisfied. No, it's not, because 5 is greater than 4 and 4 should be on top. So we swap this with this. And now we have the heap order property satisfied. Okay, I hope this makes sense. This is how you can insert items into a heap. So that now brings us to removing items. Let's look at how to remove items. Well, the method removement of the priority queue ADT corresponds to the removal of the root key. Remember that the heap, the reason why we're using a heap here is we're implementing a priority queue with a heap. So we would only ever need to remove the root, because the root would be the minimum element. In a max heap, it would be the maximum element. So in this way, we'll always want to remove the root, because the root is the minimum element. See, everything is greater than the minimum, which is at the top. And it makes sense because the heap order property facilitates this. So we now need to remove 2 because we want to remove min. We want to execute the function remove min. So how do we do this? Well, here's some instructions. I'll just tell you the instructions more arbitrarily, but you can read them if you like to. So the way you would do this is you would take out 2. So it goes, okay. You'd get the last node, okay, the last node. Okay, you get the last node and you swap it with 2. So 2 goes, 7 will now be at the top in the root. Okay, before when we inserted a new node, we had to up heap. Now that we're putting something at the top, we down heap. We need to find the correct position for 7. That's what we need to do. So the way we would do this is we would say, okay, we have 7, which violates the heap order property because 7 is greater than its children. It should be less than. So what do we do? Well, we need to find out if we can move 7 to the correct position. But where is the correct position? That's the question. So we need to do something called a down heap. To restore the heap order property, we need to restore the heap order property. So we do something called a down heap. Let's now look at how the down heap works. So we've got our 7 at the top. All we got to do now is compare 7 with the 2 children. Remember, it's a binary tree, so you got a notion of a left child and a right child. Okay, you got these 2 children. So 7, we need to pick now the smallest of the 2 children to replace 7, to swap with 7. So we compare 5 with 6, which is smaller, 5. So 5 is smaller, so we're going to replace 7 with, we're going to swap 7 with 5. So we swap 7 with 5. And then we look at now these children, we look at this subtree. So we're now assuming that all is well here. We now need to look at this subtree. So we're going to see, okay, 7 is smaller than 9. Okay, does this violate the heap order property? No. Okay, this is the heap order property. Fantastic. Okay, why? Because 7 is smaller than 9. If 7 was larger than 9, then we would look at both of 7's. If 7 was larger than its children, we'd look at both of the children. In this case, there's nothing here. Pick the smallest and swap 7 with that. So, okay, now that begs the question, what is the computational complexity? Well, looking at the computational complexity here, we see that 7 would only have to traverse, in the worst case, from the root to, if 7 was, suppose, a very large element, like 100, then it would be greater than all of the other items in the tree. And so it would need to traverse the longest path, which means it's going to go from the root, trickle down right to the leaf node, which means it's going the height of the tree. And that means it would have to swap log n times because it's a complete binary tree. So the complexity of our down heap algorithm is the height of the tree, which is log n. And that's how we can calculate it. All right. Like I said before, if you need to be convinced about the complexity, just go to the lecture on trees and you'll find how we deduce this log n. Okay, great. So this is a small procedure to update the last node, right? To find, so if you're inserting a node into a tree, you could find the place of insertion by simply going to the last node, which in this case would be here, going up the tree until you find a left child or the root, and then you just go right once and then continue to go left, and that's how you can find the new place to insert a new element. Right? This algorithm is pretty standard, and you could obviously make up another algorithm similar to this for updating the last node. Okay, it's pretty straightforward, and this is just this could be hard coded because it doesn't change; it'll always be the same. All right. So that brings us to heap sort. So heap sort is now, well, like selection sort, like insertion sort, it is a sorting procedure. What makes heap sort different is the computational complexity. It is the efficiency of heap sort that sets it apart from insertion sort and selection sort. So if we have a priority queue represented by heap sort, then let's consider what would be the time to insert items into into the priority queue. So we see that the space used, if you've got one entry for each, if you got one place in memory for each entry, then you would be ON. Okay, now you can represent the space in memory any which way you like, using linked lists, using arrays. I'll show you an example in a bit. But the point is that you would have n entries and you would have n places in memory. So the space complexity is ON. The method's insert, to insert something into the heap, is log n, and the method to remove min is log n, because remember in insert, we insert at the bottom and it trickles up until we get to the root, in the worst case, so that will be log n, and in the worst case, remove min would be taking the root out and replacing it with the last node, and then trickling the last node down the tree to find the correct position. So that's also log n. The method size, to check the size of the heap, is O1, because we can just keep a counter. As we insert items in, we update our counter +1, and as we remove items, we decrement the counter -1. Empty can be deduced from size, so we just say, well, if size is 0, then indeed it is empty, so that's O1 as well. And minimum is O1 because the root, we just have to check the root. We're not removing it, we're just checking what it is, and whatever it is, if it's a 2 or 1, we just return it. We don't take it out, we're not removing it. If we had to remove it, then we would be remove min. Okay, so using a heap-based priority queue, which is what I've shown you here, you can sort a sequence of n elements in ON log n. Now, how did we get that? Okay, so there's n items to go into the list and log n to put in those n items. Okay, so that's going to be n times log n. That's how you can implement it. And then, of course, removing those items, it'll just be plus n log n, because you're removing n items, and to remove the min of an item is log n, so you multiply it by n. So this should actually be 2n log n, but remember we say we lower order terms and constants fall away, so the 2 would have fallen away. Okay, but ideally you'll find merge sort also has a 2 here, because it builds a binary tree and then deconstructs it. But yeah, so that requires 2n log n. But I won't be too technical with you. I'll just tell you that this is the correct complexity for heaps, for heap sort. Okay, and heap sort is now it's the state of the art. It's an extremely powerful algorithm, and like I said before, you can use it to do all sorts of sorting procedures. And it's recommended to be used on larger sizes, and you could always use these smaller, much more easier to implement insertion sort and selection sort for smaller arrays. And let's leave the bigger arrays for merge sort, quick sort, and heap sort, which are the much more suited for those. And you'll find the trade-offs of using these. You can find them online, also in the textbook. So I did discuss this before in the lecture on trees, and I'd like you to go back there and have a look at this again if you didn't understand it, because we said that we could implement a complete binary tree in that lecture using a vector efficiently. And I told you that if it wasn't a complete binary tree, you'd be wasting space. And I gave the example of saying, suppose you were going to use a vector-based implementation with this notion of ranks. Left child is going to be at this position and the right child will be at this position. I said that if you are going to be doing this with binary trees, you could be very inefficient, because you could have the situation like this, where you are trying to store a chain, even if you had one here, a chain of nodes. And if you had to find the positions of these in the array using this notion, for example, if this was a 2, this would be position 0, so that would come here. Then the right child here is represented by 2i plus 1, so it'll be 2i, in this case is 1, this is position 2, this is position 3, this is position 4, this is position 5. You would have 2i plus 1, so this will be stored at position 2i, so that'll be 2 times 1, which is 2, plus 1, which is 3. This would be at position 3. Okay, so this would be here. Okay, can you guess where its right child will be? Okay, so if this is position 3, it will be 3 times 2. Okay, 3 times 2 plus 1, 7. Okay, that's going to be a position 7. 6, 7, so it'll have to come here. But my point is that for this case, it was inefficient to have this vector-based implementation of a heap. But if we assume that our array, if we assume that our heap or our binary tree is complete, if we assume that, not too sure why it's only erasing half of this stuff, then we could actually implement it in this way. We could implement it using a vector-based implementation. And so, and this is only because we have a complete binary tree. All right, so that's my point. So I'd like you to actually consider using vector-based implementations if you are implementing a heap, as opposed to linked list-based ones, because you won't be wasting space. There wouldn't be empty spaces in between, as I've discussed previously in the other lecture. So let's quickly talk about merging two heaps together. Suppose you have one heap over here, okay? You've got another heap here. You want heap 1 and heap 2. And both of these are heaps because they're complete binary trees. The last layer is leftmost, and they follow the heap order property from one heaps. If we were to merge these two heaps together with a new node k, all we would do is we would take the heap 1, which is here, and heap 2, which is here, and we would simply join them up with k, and then down heap to find the correct position for k. Okay, and then we have a heap here that satisfies all of the properties. So to merge two heaps together, you would need log n with some element k. And if you didn't have that element k, you can still do it in log n. You would just need to pick an element that is larger than all of the other elements in the tree, and then have that trickle down the tree. But then you might have to consider the exception cases, because then if you do have a situation like that, you could have a space here which you would need to fill. But I will leave you to figure that out. Okay, so this is the bottom-up heap construction, right? So you've got these smaller heaps that you join up to make a larger heap. So bottom-up means that it's going from the ground up, and you'll find that you could have smaller heaps that together give you bigger heaps. Here's an example of constructing this is the bottom-up representation. I want you to think about the efficiency of these things. So individually, each of these are heaps with one element inside of them. 1 heap, 2 heaps, 3 heaps, 4 heaps, 5, 6, 7, 8. Then you put the next layer in, okay? You put the next layer in and you down heap. Okay, so that gives you you now have smaller heaps. Then you do the same thing again, and you add the next item in. All right, and then you're gonna down heap again this way. Then you put the last item in. So all the while you're keeping track of these heaps. These are smaller heaps, but together, once you find the correct position for 7 in this case, or 8 in this case, you are creating more heaps, bigger heaps. So this is a bottom-up way of doing it. There is a top-down way of doing it. I want you to figure out which is the cheaper way of doing it. So in this case, you have the last element which trickles down right till the end, and this is also log n. And then this is the way of creating a heap. So spend some time to think about what is better. Now look, I mean, it's really useful to think about how to build the heaps, because if you have the number of elements predefined, you can work out the structure of the heap before you even put anything in. So you could have the last layer constructed. If you do it bottom up, your last layer is heaps, then you build up, going layer by layer from the bottom to the top, and work out the complexity of it. Now, there's a little clue here, as well as a nice intuition for how to do it. Just go through it, and you find that each of these heaps themselves, each of these smaller heaps, the log n isn't as big as the log n for the entire heap. So these smaller heaps get subsumed in it, and then you end up with a total complexity of on. But I would like you to think about this in contrast to building the heap by inserting an element one by one. So looking at the bottom up, just to recap, looking at the bottom up reconstruction, as opposed to looking at the construction where you add elements one by one, growing the heap in size. And